So to continue this concept, let's quickly look at a couple of profiles in the ocean. Here we are showing oxygen in moles per microliters, or moles micromoles per liter, sorry, and CO2 in microatmosphere. So it's dissolved CO2, so you can think of its partial pressure in microatmospheres. And this figure is showing the North Pacific and the North Atlantic. Why? We will see later on that the two oceans are very different because of certain processes that happen, and this actually turns out to be very critical for climate at various time scales. So the main features we'll look at here will be related to what you kind of intuitively have an idea about. Why there are these large differences in the two oceans will become clearer later on as we add more processes to our understanding after we go into what are the processes that are creating these differences, right? So if you look at oxygen, it's higher near the surface. Why? You can imagine two processes. One is because oxygen is high in the atmosphere and it's probably constantly mixing oxygen into the surface water, which is true. What else is happening? Near the surface you have a lot of sunlight, and if you have nutrients available, there is going to be photosynthesis in the ocean. Phytoplankton, which are in the ocean, which are photosynthesizers, which are the primary producers which supply the food chain in the ocean, are photosynthesizing, which means they are producing oxygen near the surface where there is enough light for photosynthesis. Okay, so this is why the oxygen concentration is higher near the surface. As you go deeper down to about a kilometer, oxygen continuously decreases. Why? Because all this photosynthesized material that's falling down is being eaten by other things like zooplankton, small fish, bigger fish, and so on. What do the species that eat these primary production do? Just like us, we eat something, we respire it to produce energy, which means we are converting carbohydrates and sugar into water and carbon dioxide, and we're doing that by breathing in oxygen. We're consuming oxygen. The same thing is happening in the oceans. All the organic matter that's being produced by photosynthesis or the dead animals that are falling down are all being respired. They're consumed below the surface, and that kind of minimizes or maximizes oxygen consumption at 1 kilometer and minimizes the oxygen concentration at 1 kilometer. As you go deeper, temperatures decrease and pressure increases as you go deeper in the ocean. Obviously pressure increases as opposed to the atmosphere, where as you go higher into the atmosphere the pressure decreases. More and more water is being stacked on top of you as you go deeper. That increases the pressure, and we will see later on that the North Pacific has a increasing concentration of oxygen with depth, whereas the North Atlantic has generally higher oxygen and then nearly constant with depth, much higher than the North Pacific. We'll see why these differences arise, but just remember that there is something called the oxygen minimum zone, generally referred to as OMZ or OMZ, at about 1 kilometer because of this heterotrophic respiration. Autotrophs are those that produce the energy, heterotrophs are those that consume the energy. So if you can immediately jump to CO2 and understand why CO2 is minimum at the surface and increases with depth, we will again see the difference between the North Atlantic and North Pacific, which is like the mirror image of oxygen. Oxygen is high in the North Atlantic, but CO2 is low in the North Atlantic. Oxygen is low in the Pacific, but CO2 is high in the North Pacific. Nonetheless, the CO2 is low at the surface. There is atmospheric exchange, but CO2 is being consumed for photosynthesis, and all the heterotrophic respiration that's consuming the oxygen at 1 kilometer is releasing all the CO2, so you have maximum CO2 at about 1 kilometer. As you go deeper, CO2 decreases. You have to also remember the analog of, let's say, a can of Coca-Cola or Pepsi. What do we do in Coca-Cola and Pepsi? We put put CO2 into water along with sugar, and we put it in high pressure and we seal the can, and we tend to keep it cool because cool waters under pressure dissolve CO2 and keep it. If you open the can or if you let it warm, CO2 is going to be released, right? So this is what happens deeper in the ocean as temperatures get colder and pressure increases. The solubility of CO2 also increases. So there are biological processes and there are physical chemical processes together that are going to determine these profiles. So these profiles should be etched in your mind. We'll also look at nutrient profiles later on, but CO2, oxygen minimum zone, sorry, oxygen maximum at the surface, oxygen minimum zone at 1 kilometer, CO2 minimum at the surface, maximum around 1 kilometer, depends on whether you are in the North Pacific or North Atlantic Ocean, and so on. So we'll stop this here and come back to defining pH in a minute, but it turns out that pH